Let's now look at the concept of linear superposition applied to sound waves. Imagine that two speakers in the same room are producing sound waves of the same amplitude and frequency with a wavelength of 1 meter. And let's assume that each speaker vibrates in phase, which means the diaphragm of each moves in and out at the same time. The sound waves from each speaker will overlap at many points in the room. If the distance from the overlap point to each speaker is the same, say 3 meters as shown in the figure for example, then the condensations of one wave will meet the condensations of the other. Likewise, the rarefactions of each wave will meet the rarefactions of the other. According to linear superposition, the combined pattern will be equal to the sum of the individual patterns. As a result, the pressure fluctuations at the overlap point add, and the amplitude is twice as large as the amplitude of the individual waves. A listener located at this spot would hear a louder sound than if only one speaker was on. When two waves always meet condensation to condensation and rarefaction to rarefaction, or crest to crest and trough to trough, they are said to be exactly in phase and to exhibit constructive interference. Now consider what happens when one of the speakers is moved. Let's move the left speaker farther away by a distance equal to 1/2 lambda, or half a meter. Even though the speaker is now farther away from the overlap point, we will assume the amplitude of its sound wave remains equal to that from the other speaker. Due to the extra distance, the condensations from the sound waves arriving from one of the speakers overlaps with the rarefactions from the other speaker. The principle of linear superposition indicates that the net effect is a cancellation of the two waves, resulting in a zero amplitude. The condensations and rarefactions canceling each other leave only an area of constant pressure. This means that a listener at the overlap point would not hear any sound. When two waves always meet condensations to rarefaction, or crest to trough, they are said to be exactly out of phase and to exhibit destructive interference. When two waves meet, they interfere constructively if they always meet exactly in phase, and destructively if they always meet exactly out of phase. In either case, this means that the wave patterns do not shift relative to one another as time passes. Sources that produce waves in this fashion are called coherent sources. In general, the important issue is the difference in the path lengths traveled by each wave in reaching the overlap point. For two waves vibrating in phase, a difference in path lengths that is 0 or an integer number, 1, 2, 3, etc., of wavelengths leads to constructive interference. And a difference in path lengths that is a half integer number, 1/2, 1.5, 2.5, etc., of wavelengths leads to destructive interference. Likewise, for two wave sources vibrating out of phase, a difference in path lengths that is a half integer number, 1/2, 1.5, 2.5, etc., of wavelengths leads to constructive interference, and a difference in path lengths that is 0 or an integer number, 1, 2, 3, etc., of wavelengths leads to destructive interference. The figure below shows two speakers at fixed positions and how their sound waves overlap. As a listener moves about the room, he or she will detect the effects of constructive and destructive interference. Whenever the condensations of the two waves overlap, the listener will hear a loud sound. Whenever the condensations and rarefactions of the two waves overlap, the listener will hear no sound at all. At locations where neither constructive nor destructive interference occurs, the two waves partially reinforce or partially cancel depending on the position relative to the speakers. Thus, it is possible for a listener to walk around the overlap region and hear marked variations in loudness, including complete dead spots, where no sound is heard. As a final note in this section, let's think about energy. We know all waves, including sound waves, transport energy. At locations that satisfy the destructive interference condition, the resulting wave has zero amplitude, and thus zero energy. We can't destroy or create energy, so where does the energy go? It goes into the regions that satisfy the constructive interference condition. Therefore, the process of superposition, along with the constructive and destructive interference conditions, redistributes the energy, as energy must always be conserved.